Remember that we left the stock prep area as the stock entered the headbox manifold. Most headbox manifolds are tapered like this, so the pressure remains the same across the manifold even as the stock leaves the manifold to enter the headbox. The job of the headbox is to spread the stock uniformly across the width of the paper machine, and that width can be very wide, up to 10.5 meters or over 400 inches. Remember that the stock is very dilute at this point, less than 1% consistency. However, fibers still have a tendency to flock together, and the headbox must break up these flocks before the fibers are deposited on the forming wire. Older type air-padded headboxes like this one used slowly rotating perforated rolls called rectifier rolls to break up fiber flocks. More modern hydraulic headboxes rely on hydraulic shear to accomplish the same thing. In either case, the stock must exit the slice opening of the headbox uniformly dispersed and with the same amount of stock at each point across the width of the slice opening. Not such an easy task. In the past, the papermaker would vary the slice opening with slice screw adjusters to correct for heavy or light streaks in the sheet. More modern headboxes use something called dilution control to do the same thing. You'll learn more about that in the module on the paper machine wet end. Okay, now that we've deposited the stock on the forming wire or forming fabric, the first real step in papermaking begins, and that is, well, forming the sheet. Remember that we have only 1 part fiber to 99 parts water, so we have a lot of water that needs to be removed from the sheet. By the time the sheet leaves the forming section, the sheet consistency will be more like 20%, meaning 1 part fiber for every 4 parts of water. That's a lot of water that drains through the wire, most of which is collected in the silo and used to dilute the incoming thick stock from the machine chest. So most of the water in the forming section just goes around and around, diluting thick stock to paper-making consistency, draining through the wire, and then returning to dilute more incoming thick stock. When the stock is first deposited on the wire, the water drains from the fibers very easily. We use gravity foils in this area of the forming section to assist drainage. But eventually the sheet will not lose much more water unless we apply greater forces than gravity alone. The first step is to enclose the foil units and apply a low vacuum, but that only works for a while, and then we need to increase the vacuum in the flat boxes. At the end of the forming section, the sheet is still very wet, maybe 15% fiber and 85% water, and it's also very weak. We have one last way to suck out more water, and that's with a vacuum-assisted roll called the couche. The couche roll has a rotating outer shell with holes and an inner fixed-position vacuum chamber. After the couche, the sheet may be 20 to 25% solids and much stronger, so it can be peeled from the forming fabric. To this point, we've shown pictures of forming sections for Fourdrinier paper machines, and that's because Fourdrinier machines, named after the original financial sponsors, are still the most common. Fourdrinier machines have a single continuous forming wire, and all the drainage is in one direction, that is, downward. Since the forces on the top and bottom of the sheet are not the same, the resulting paper is not the same on the top and the bottom. Not much of a problem in the past, but it can be nowadays. Most modern high-speed paper machines are twin-wire design. Twin wire means the jet from the headbox is trapped between 2 forming fabrics, so that drainage occurs in 2 directions. Two-direction drainage means the sheet of paper is much more similar on the top and the bottom. It also means the paper machine can run much faster because the stock can't jump off the wire at really high speeds, as it can on a Fourdrinier machine. What's really high speed? Most grades of paper can be made at over 2,000 meters or about 6,500 feet per minute. That's 120 kilometers or 75 miles per hour. Maybe not fast enough for Le Mans, but pretty quick for making paper. And that's not the end. Paper machines of 3,000 meters or almost 10,000 feet per minute are already on the drawing board. Well, now that we've formed the sheet, what happens? There's still a lot of water that needs to be removed, and the way to do that is by mechanical pressing. A press consists of 2 rolls and 1 or 2 press fabrics, or felts. The sheet lies on the press felt and is carried through the nip of the 2 rolls, where the hydraulic forces push the water from the sheet into the felt. Then the felt carries the water away from the press nip, and the water is removed from the felt through a vacuum slot called an Ullbox. A press section consists of several press nips, sometimes in a cluster arrangement, and sometimes just straight through, as the papermaker would call it. The job of the press section is to remove as much water as possible, because the next step, that is removing water by drying the sheet, is much more expensive. Remember that the sheet is entering the press section at somewhere around 20% consistency, or 20% solids and 80% water. The sheet is still very weak, so it is supported as much as possible by the felts, especially on high-speed paper machines. By the time the sheet has left the press section, the sheet solids are over 40% and maybe as high as 50%. Higher sheet solids are possible due to new press rolls called shoe presses, which are not rolls at all but hydraulic rams. You'll learn more about them in the module on the dry end. But no matter how much we press the sheet, the cellulose fibers are still going to hang on to a lot of water. And the only way to remove the rest of it is through thermal forces, that is, drying the sheet against steam-heated dryer drums or dryer cans. Dryers are cast steel or cast iron cylinders which are filled with steam. As the sheet wraps around the dryer, the temperature of the water in the sheet rises until the water turns to steam vapor and leaves the sheet. Inside the dryer, the steam has transferred its energy to the inside surface of the dryer, so it turns back into water called condensate, which is removed from the inside of the dryer through a siphon. Any steam that escapes through the siphon is reused in the dryers, and the condensate is sent back to the boiler to be turned back into steam. If it's done right, the thermal energy is very efficiently used. But it's important to know that drying the paper with steam is still one of the most expensive operations in both the pulp and paper mills. Once the paper is dried to 5 to 7% moisture, it can be wound up and removed from the paper machine. But for most grades of paper, there are several more operations that occur in order to change the physical properties of paper. One is surface sizing, and the other is calendaring. Surface sizing happens first, and that process occurs on the size press. The size press is located in an open space between dryers toward the end of the dryer section. The sheet coming to the size press must be very dry, usually less than 5% moisture. The size press is made up of two rolls nipped together much like a press, but with minimal pressure between the rolls. The purpose of the size press is to apply a thin solution of cooked starch to the sheet to improve sheet strength and printability. Older size presses had a puddle of starch in the nip between the two rolls, and the sheet passed through the puddle. More modern metering size presses apply the starch to the surface of the two rolls and allow the rolls to push the starch onto the sheet. Along with the starch, the sheet picks up water, so that water must be removed with the remaining dryers. Now we're almost at the end of the paper machine, but for almost all grades of paper, we need to calendar the sheet before it can be wound up on the reel. Calendaring is similar to ironing a shirt since it smooths the surface. Calendaring also improves the uniformity of the thickness or caliper of the sheet. In other words, the calendar rolls push down the high places in the sheet so they're closer in thickness to the thinner places in the sheet. Calendar stacks used to be made up of 2 or more hardened rolls, but many grades of paper are now produced using soft nip calendars where one roll is hard and the opposing roll has a soft polyurethane cover. The soft cover conforms more to the surface characteristics of the sheet to produce a better surface for printing. Finally, we are at the end of the paper machine and can wind up the web of paper. We discussed that paper machines don't often stop, so a method had to be developed to wind up a large roll of paper and then remove it from the paper machine without interrupting the operation. And the way we handle that is with the reel. The reel is made up of a large steel or cast iron drum, a set of rails, 2 sets of arms, one called the primary arms and another called the secondary arms, and a number of reel spools. When the paper roll being wound has reached its maximum diameter on one reel spool, the sheet needs to be transferred to an empty reel spool. This operation, called a turn-up, starts when the empty reel spool in the primary arms is speeded up to match the web speed, and then lowered on top of the web as it's being pulled across the reel drum. Now the tricky part occurs. The paper web must now be broken so it can wrap on the empty spool in the primary arms, while the full jumbo roll is simultaneously released from the reel drum. There are several ways that this web break can happen, sometimes with a jet of air, sometimes with a tape. But when it happens quickly. Now that we have the paper on the new spool, the primary arms lower the new spool to the rails and the secondary arms take over. Then the primary arms can be returned to their upright position to accept a new empty spool. How often this process occurs depends on the grade of paper, the speed of the paper machine, and the allowable size of the jumbo reel. But a normal time between each turn-up is around 45 minutes. Now that we have a completed reel, called the jumbo or parent roll, what do we do with it? For most paper machines, the answer is that the parent roll must be cut down into small rolls that are sold to the customer, or in some cases sent for further processing in the paper mill. This is a 2-drum winder that usually does the job of rewinding the paper. The parent roll is threaded through the winder and attached to paper cores that are cut to the width of the new rolls. Sharp rotating knives called slitters cut the paper as it's being wound on the paper cores. When the new rolls reach the required diameter, the winder is stopped and the rolls are ejected from the winder. Often it's possible to make 2 or 3 sets of rolls from one parent roll, which saves time in rethreading the winder. And time is really critical in the winder operation. Remember that although the paper machine doesn't stop, the winder is required to every time a set of rolls is ejected. Add in time to thread the winder, attach the sheet to the cores, set the slitters to the correct width, and acceleration and deceleration time, and you can see that the winderman's job can be a pretty hectic one. And if that isn't enough, think about an accidental web break while the winder is operating at top speed of perhaps 3,000 meters or 10,000 feet per minute. No wonder the winder has become the most automated piece of equipment in the paper mill. This ends the lesson on the overview of the paper mill. Pulp enters the paper mill either